Okay, YouTube, in my last video we looked at the rational roots theorem, and in this video we're going to put it to use in finding the zeros of a couple of polynomial functions. So we've got a couple of third degree functions here that we're going to solve for the zeros of, but we see here that if we were to set this equal to 0 here, or I hope you see this, if we try to factor this, say factor it by grouping, and maybe I'll rewrite this here, I just want to show you this. If we try to factor this by grouping, oops, I should keep that positive there and put a plus here, we get something that doesn't actually factor well for us here, or at least I can see that only thing these two things have in common are 1 here. So when we look at this, this and this are not the same, and this thing just basically doesn't factor by grouping. So let's see if I can get rid of all of this here. Hopefully I can. So we're going to use division to our advantage. So the question is, well, what would divide out of this evenly, or what are its zeros? Well, I can't erase this here, but we would say we'll start by making a list of things that could possibly work if they're rational. So we say plus or minus. Remember, this is the factors of the constant term over the factors of the leading coefficient. So factors of 20, there are a lot of factors of 20. We could say like 1 times 20, 2 times 10. I suppose 4 times 5 would be factors here. So 4, 5, and 2 times 10, and then 20. That's a lot of factors. And then we say, okay, well, factors of leading coefficient are 1. So when we rewrite this list, just because we want to have it in roster notation, I think everything over 1 would be 1, 2, 4, 5, 10, and 20 could potentially work if you're a rational 0 at least. You have to be on this list. So what we're going to do is we're just going to basically find something that leaves a 0 remainder when we divide it out here, or at least find a 0 of this function. That means when we plug this in, we would get 0 for an output down here. At least that's what we're looking for. So we'll try with x equals 1 here first. And we'll go ahead and drop in our coefficients. Let me get that out of the way first. 1, 8, 11, and negative 20. And I'll extend this a little bit here. So we'll try with 1. And dropping down our 1 here, we would get this. 1 times 1 is 1, plus 8 here is 9, times 1 is 9. And then we get 20 here. 1 times 20 is 20. And so we do end up indeed having a 0 remainder. So a few things I want to say about this. Maybe I should write an equal sign here. Remember that this is the same thing as what we get for a y value when we plug this in for our x value up here. But that also means that zeros. We just found one. We're going to list it here. We say x equals 1 is one of our zeros of this function. Furthermore, what I want you to understand is that this is the quotient, okay, whereas this is our remainder expression here. And so because we have no remainder, we could say that what we were really dividing out here, if x equals 1, was the factor was x minus 1. And our quotient here when we write it is x squared plus 9x plus 20. So I know that if I were to take this times this, I would get back to the original statement. So that is to say that our original f of x here could be written as x minus 1 times our quotient that we had left over, x squared plus 9x plus 20. And if I'm setting all of this equal to 0, essentially what I want you to see is that one of these we don't need to really set equal to 0. That's this first one right here, because we already were able to determine that is a 0 of this function. But I do want you to see that we would indeed set this equal to 0, but this is something that itself factors. So if we were to say, let's factor it, I would have my x minus 1 out in front still. I'd say, well, two numbers that multiply out to be 20 that add up to be a 9 would be 5 and 4. And so at this point, you see how just finding one of these factors on the list, we just guessed and it worked. Then I was able to factor to get the other two factors on the list. And so that would tell us that the other two zeros here, if we set x plus 5 equal to 0 and solve, we get x equals negative 5, of course. And if we were to set x plus 4 equal to 0, we get x equals negative 4, of course. Sorry for the handwriting here. So we say all of our zeros together are 1, 5, and negative 4, and this third degree function had 3 zeros. So let's look at this now, third degree function down here. I noticed that it doesn't factor as well, and I'm not going to show why that doesn't work. I just noticed that it doesn't. So we're going to start with our list of possible rational roots that might work, that we could guess from. So we're going to say, well, all the factors of our constant term is 2, so we have 1 and 2 are its factors, and then our leading coefficient is 1, so I really didn't need to make that as big as that. We say 1 and 2 are the only possible rational roots that might work on this function. So let's just see if we can get any to go in evenly. So we have 1, 1, negative 5, negative 2. On the outside of here, I always start with 1. Just, I think that it's a good idea. And so we say 1 times 1, we would get 1 plus 1 is 2 times 1 is 2, plus our negative 5 here, I already noticed that this isn't going to work here because we're not going to get a 0 remainder. So let's back it up. I know you can't do that on your paper, but I'll go with negative 1 now. Let's try this. So negative 1, if 1 doesn't work, maybe negative 1 works, and that's on our list over here. So negative 1 times positive 1 is negative 1, plus this is 0 times that is 0, plus this is negative 5, and that's not going to work either here. So you know what? If 1 and negative 1 don't work, let's try this. Let's scratch this out. We'll try positive 2. 2's on our list over here. And so 2 times 1, of course, is 2, plus 1 is 3. Times 2 here is 6, plus this here gives us a positive 1. This is hopeful here. So I notice that I get this here, which would give us a 0 remainder. So in terms of zeros, let's make our list. These are the answers we want anyways. I just found out that 2 is a 0. I found out that when I plug 2 into the function, I get a y value 0, so it's an x-intercept. And I also know that that means that x minus 2 is a factor. So if x minus 2 is a factor, then this right here, this x squared plus 3x plus 1 is the quotient, and when I multiply those together, I get my original f of x. So the reason why this is important is because now this we can just factor on our own. If it's factorable, I think it may not be factorable in this case, but if it's factorable, we'll do it on our own. I cannot think of two things that multiply out to be a 1 though, that add up to be a 3. So here's what we're going to have to do. We're going to have to use our quadratic formula. So here's the hopeful thing though. When you divide this first degree thing here out of your third degree thing, you get left with a second degree thing, but whenever you're left with a second degree thing, be rest assured that you can always solve it because you have your quadratic formula if you need it. So we say here our a is 1, our b is 3, and our c value is 1. So with our quadratic formula, I'll try to write small here. We have negative b, and our b value is 3 here, plus or minus the square root of b squared, so 3 squared minus 4, times our a value is 1, times our c value is also 1, and this is all over 2 times a, which our a value is 1. So simplifying this here, we have negative 3, and this is all over 2, of course, but plus or minus the square root of. Now, when we simplify this in here, I get 9 minus 4, so I get a 5. So my two roots, my two other zeros here, would be negative 3 plus or minus the square root of 5 all over 2, and we could certainly find this on a calculator, but here's what I know. When you list your zeros, which I feel really bad because I had a good list going right here, and then I tend to write over the top of things. I would list them as 2 and then negative 3 plus or minus the square root of 5 all over 2. And certainly feel free to get decimals for these, but I noticed that I got 3 zeros for this third degree function, which will play importantly into the next things we do. Cheers.